For each of the following differential equations, state whether it is linear or nonlinear, and also whether it is homogeneous or non-homogeneous. So looking at all of these y's, we can see that they are by themselves. They are not inside of anything, and they are not touching another dependent variable. So A is linear. For B, if we look at these y's, we see that this one and this one are fine. However, the middle one is what causes B to be non-linear, because this y prime is multiplied by a y, and when that happens, it is non-linear. For C, we're going to look at the y's again because they're the dependent variable, and looking at them, they're not inside of anything nor are they touching anything, which means it is also linear. For D, we're going to look at the y's as they are still the dependent variable, and since they are by themselves, not inside of anything and not touching another y, it is linear. Now to determine homogeneous, or if it is non-homogeneous. For A, we can see that all of these values have y's in them, which means they have to stay on the left side, meaning the right side is 0. As long as the right side is 0, that means it is homogeneous. For B, because it is nonlinear, it cannot be homogeneous or non-homogeneous. If it's nonlinear, it is just nonlinear. Only if it's linear can it be either homogeneous or non-homogeneous. So we'll put not available. For C, this y stays on the left side, this y stays on the left side. However, this sine of x, it does not have a y connected to it, which means it must move over to the right side, which causes the right side not to be equal to 0. That means it is non-homogeneous. For part D, this y stays on the left side. All of this connected to the y stays on the left side as well because it is connected to a y. However, for the right side, we can see that this material does not equal 0, and it does not have a y in it, which means it is non-homogeneous. So A is linear non-homogeneous, B is non-linear, C is linear non-homogeneous, and D is linear non-homogeneous. For problem 3, we're asked to determine whether a unique solution is guaranteed to exist for the following initial value problems on the given interval I, and explain your answer. So if we first look at A, we see this. Now, there's a few steps that we have to do. The first is we have to make sure all of the x values, whatever is in front of y, basically, this value, this value, this value, this value, and this value as well. All of that has to be continuous on the interval. The interval here is negative infinity to infinity, so we have to check that. That will be step 1. So if we check that for this first part, x squared y triple prime, we get that it is continuous. So this is good. For x y double prime, this is also going to be continuous on negative infinity to infinity. Sine of x is also continuous on negative infinity to infinity. X is continuous on negative infinity to infinity, and 0 is just 0 on negative infinity to infinity. So it passes that test. Our second test is we need to make sure the first value in front of y, we need to make sure that this value does not equal 0 on the interval. Well, if we look at it, the interval goes from negative infinity to infinity. That means that it does hit 0. So it fails this test. The third test would be to make sure that these values exist on the interval, or that they exist in the interval, that they are included in the interval. However, since step 2 does not work, we are not guaranteed a solution on the given interval. And you could write your answer like that and circle it, pointing to the step that failed. Looking at part B, we will do the same 3 steps. First, we will check to see if it is continuous. Second, we will make sure that the first value does not equal 0 on the given interval, and third is to make sure specific values are in the interval. For step 1, we need to make sure this value, this value, this value, this value, and this value are all continuous on the interval. We can see that our interval is from 0 to infinity. Checking continuity is step 1. For x squared, it is continuous from 0 to infinity. X is continuous from 0 to infinity. Sine is continuous from 0 to infinity. X is continuous from 0 to infinity, and 0 is just 0 from 0 to infinity. Now for step 2, we need to make sure a of n, so whatever value a is here, it does not equal 0 on the given interval. Well, the interval is from 0 to infinity. However, because it is a parenthesis and not a bracket like this, it does not include 0. If it was written like this, that means it would include 0, and it would not work here. However, since it is just a parenthesis, that means it does not include 0. So basically it means it starts from 0.1. That's not correct, but you can think of it as like that. It starts from 0.1 and it goes to infinity. So x squared does not equal 0. For step 3, we need to make sure the given values are in the interval. So we need to check if these values are in the given interval. So the given values, it's just 2. So we need to make sure this value is included in the interval, only this x value. And when we look here, our interval is from 0 to infinity. 2 is included in 0 to infinity. So that passes this test. We can write it like this, showing that 2 is in here, which means this is checked. That means we are guaranteed a unique solution. After you show all the steps, you can write something out like that and circle it. For part C, we're going to do the same thing. We need to check continuity, ensure the first value in front of the first y does not equal 0 on the interval, and we need to make sure the given x values are in the interval. So step 1 is checking continuity. So we look at this first value, it's just going to be 1 since it's empty. We need to check this value, and this value. All these values have to be continuous on the interval. 1 is always going to be continuous because it's just going to be 1. X is going to be continuous. X squared is going to be continuous. However, when we look in front of the y prime, we see a problem. If our interval is from 0 to infinity, this includes 2. So if we write it like this, we can see that 2 is in our interval. If we plug in 2 here, we get 1 over 0, which is not continuous. This means we are not guaranteed a solution. And we can write it out like this. So this will be our answer. Since 1 over x minus 2 is not continuous on I, we are not guaranteed a unique solution. It fails the first test, which means we are not guaranteed a solution. For D, we're going to do the same steps. Check if it is continuous on the interval. Make sure that our first value does not equal 0 on the interval. And step 3 is to ensure that our given values are included into the interval. Step 1 is to check continuity. In front of our y prime is a 1. In front of our y is a tangent of x. And to our right, we have an x squared. This has to all exist on the interval 0 to pi over 2. On this interval, 1 is just going to be 1, so that's fine. On the interval, x squared also exists. For here, tangent, it also exists. For step 2, we need to make sure our a of n, which is our first value right here, does not equal 0 on the interval. Well, it equals 1, so it cannot equal 0. So this step passes as well. For our last step, we need to make sure our given value is in the interval. This value is actually called x naught. And in B, these values are x naught. I should have stated that earlier. But this is what we label them, and we have to ensure that it is in the interval. Is pi over 2 in the interval? Well, when we look at this, recall what we said about parentheses. The fact that these are parentheses means that it gets very close to but does not touch these values, which means that pi over 2 is not included in the interval. If it was written like this, it would be included in our interval. However, since it is not written like that, it is not included. And we can write the answer out like this, that we are not guaranteed a unique solution since x naught is not in I. You can point an arrow to this. X naught is more written like this as well. For question 4, we're asked to find a large interval for which a solution to the initial value problem y prime plus 1 over 1 minus e to the xy is equal to sine of x is guaranteed to exist and be unique. For something like this, we need to look at the values in front of the dependent variable, which in this case is y. So in front of y prime is 1, and in front of y we have 1 over 1 minus e to the x. We also have to look at the right side, which does not have a y, and in this case it is sine of x. So what we need to do is find the largest interval. In finding the interval, it needs to exist from negative infinity to infinity. After we know this, we can start checking the values. So first, we're going to check what is in front of y prime. The only thing in front of y prime is 1. And 1 is just 1 on 0. So the first thing that we're going to check is what's in front of this y prime. The only thing in front of this y prime is 1. And 1 is going to be 1 from negative infinity to infinity. So this interval is negative infinity to infinity. Next, we're going to look at what is in front of y. So for this, we're going to look at 1 over 1 minus e to the x. When we're looking at this, it is not continuous at one point. And we can find this by setting the bottom equal to 0, because the bottom cannot equal 0, since anything over 0 is not allowed. So from here, we're going to get e to the x is equal to 1. If we take ln of both sides, we get x is equal to 0. So that means x at the bottom cannot equal 0. So this interval exists from negative infinity. This exists from negative infinity to 0, and also on 0 to infinity. Lastly, we're going to look at sine of x. Sine of x is continuous for any value from negative infinity to infinity. So that means the only thing that we have to worry about is this value right here. So since it's asking us for only one interval, find a largest interval, that means we can only pick one of these. And in this case, it can be either. So the answer could be this, or it can be this, just not both. So we'll pick the answer to be 0, infinity. If you are given an x naught value, let's say x naught is equal to -5. If we are given this with our question, that means this would have to be the answer, since -5 only exists from negative infinity to 0, and it does not exist from 0 to infinity. If we were to get x naught is equal to 1, we would have to use 0 to infinity, because 1 only exists on 0 to infinity, and it does not exist from negative infinity to 0. Number 5 asks us to find the Wronskian of y1 is equal to cosine of 3t and y2 is equal to sine of 3t. So the formula for a Wronskian is w y1 comma y2 is equal to the determinant y1 prime y2 y2 prime. So after we have this, we can just start plugging in values. So we have our y1 right here. So that's going to go in here, and then we're going to plug it in here as well. We also have our y2, which is going to go here and here. So from here, we're going to have cosine of 3t right here. We're going to take the derivative and get negative 3 sine of 3t. We have to use the chain rule. And we're going to do the same thing for this side where we have sine of 3t, take the derivative, and we get cosine of, actually, that should be 3 cosine of 3t because of the chain rule. Now from here, we have to use this, y1 times y2 prime minus y1 prime times y2. And the way you can remember this is by multiplying like this. So you start from up here, you start at the top, and you kind of do like a cross product where you multiply this y1 by the y2 prime, and then you come and you start again here, and then you have y1 times y, or you have y1 prime times y2, and that's going to equal this, and you have to have a negative sign in front. So when we do this, we're going to get cosine of 3t times 3 times cosine of 3t minus negative 3 sine of 3t times sine of 3t. For the cosines, we can combine both cosines to be cosine squared of 3t, and with the sines, we can combine those and have sine squared 3t. After we do this, we are just moving the 3's to the front, and we are making these negative signs. We are combining the negative signs together to form a positive. So from here, it's important to remember this rule. And that rule is that cosine squared of theta plus sine squared of theta is equal to 1. So after we write this down, we can see it's almost identical to what we have. All we have to do is factor out the 3 and substitute the theta for 3t, and it's exactly the same. So all we're going to have is 3, since cosine 3 of t plus sine of 3 of t is equal to 1. And that is the answer. For number 6, we're told to suppose the following functions are solutions to differential equation. We're asked to determine whether they are linearly independent solutions on the given interval. That means we need to use the Wronskian. And after we use the Wronskian, we're going to get some value. If this value is equal to 0, that means the solution is linearly dependent. If it is not equal to 0, it is linearly independent. After we plug our values in, for a, we're going to get e to the 2x for y1. y1 prime is 2e to the 2x. y2 is e negative 3 over 2x, and y2 prime is negative 3 over 2 e negative 3 over 2x. Plugging in all of our values, this is what we get. When writing this out, we have to go from top left to bottom right, and then bottom left to top right. So after we write this out, we can see a couple of things. We can see that e to the 2x is on both parts. E negative 3 over 2x is also on both parts. So that means we can factor these out. After we factor these out, we're just left with a negative 3 over 2 and a negative 2. Combining those, we get negative 7 over 2. And on the outside, we have this e to the 2x times e to the negative 3 over 2x. Since they're both e's, we can add them together. So it'll be e 1/2 x. So this is what we get for the Wronskian. Now, this does not equal 0 on any interval. Properly write this answer, we need to state that it does not equal 0 on the interval. Therefore, it is linearly independent. If it were to equal 0 on the interval, it would be linearly dependent. But since it does not, it is linearly independent. For part B, we're using the values y1 is equal to e to the x, and y2 is equal to 3ex plus 2 on the interval 0 to infinity. Plugging these into the Wronskian, y1 goes here, y2 goes here. Now we need to take the derivative. So the derivative of e to the x is just e to the x. And the derivative of 3ex plus 2 is 3ex plus 2. When we plug all this in, we see that we have e to the x, 3e x plus 2 minus e to the x, 3e x plus 2. Since these are both equivalent to each other, and we have a negative sign in the middle, this means this equals to 0. The answer for this is that since it equals 0 on the interval, it is linearly dependent. For part C, we're given y1 is equal to x, and y2 is equal to x e to the x on the interval -5, -2. We need to plug in our y1 here and our y2 here. Taking the derivative of x is just 1. Taking the derivative of x to the e of x is e to the x plus x e to the x. An easy way to do this is combine these, so factor this x in here, and then subtract this part. So after we factor our x in, we're left with this. We also have this part. So what we're going to do is cancel out this with this, and we're just left with x squared e to the x. Now our interval goes from -5 to -2. The only way for this to equal 0 is if x is 0. However, however, 0 is not included in the interval. If the interval went from -5 to 2, it would be linearly dependent since it does equal 0. Since it does not equal 0, or since 0 is not in the interval, it is linearly independent. And we can write it like this. Since x squared e to the x does not equal 0 on the given interval, it is linearly independent. For number 7, we're asked to verify that y1 equals 1, y2 equals cosine of t, and y3 equals sine of t are solutions to the differential equation y triple prime plus y prime is equal to 0. Do these solutions form a fundamental set of solutions for this differential equations? So to first verify, we need to plug all of our y's into the equation. So writing out y1, we get that the first derivative is 0, and the third derivative is also 0. And 0 plus 0 is equal to 0, so this is a solution. So for y2, we get that the first derivative is negative sine of t, and the third derivative is sine of t. Negative sine of t plus sine of t is equal to 0, so this is also a solution. For y3, if we take the first derivative, we get cosine of t, and the third derivative being negative cosine of t, cosine of t minus cosine of t is equal to 0. Therefore, this is also a solution. So step 1 was to verify that all these solutions are solutions to the differential equation. Step 2 is, are these solutions a fundamental set of solutions for the differential equation? For this, since we have y cubed and we have 3 y's, we can use the Wronskian and see if it is a solution. So once we write out our Wronskian, this is what we get, and this is how we do it. We have to use the y1, y2, and y3 in here. So as you can see, we have our y1 column, y2 column, and y3 column. And to solve this, we're going to have a bigger part that we need to plug in our values for, and that is this. So all the values we need to plug in, we'll find here. What we can notice though, what we can first do is look at these zeros. So both of them are in f1 prime and f1 double prime. So if we find our f1 prime, which is here, we can cross this out because this is 0. And our f1, we have another f1 prime here. This crosses out to be 0. We have an f1 double prime, so this is also 0. So this entire thing is 0. We have our f1 double prime here, and that's 0. It's going to be 0. And then let's see, we just have an f1 here. So that means we're going to have 1 and parentheses negative sine t times negative sine of t minus cosine of t times negative cosine t. What we can do here is combine these negatives to make a positive, make this sine squared of t, and then make this also into positive, so we have plus cosine squared of t. And sine squared of something plus cosine squared of the same thing is equal to 1. So our final answer is going to be 1. This is what we get from our Wronskian. And from an earlier, we remember that if the Wronskian is equal to 0, it is linearly dependent. If it is not equal 0, it is linearly independent. Since 1 does not equal 0, that means we get a linearly independent solution. Since it is linearly independent, that means we are guaranteed that these solutions form a fundamental set of solutions. Number 8 is asking us to solve the following differential equations and find the general solution. So for this, if anything is in this form where it's y to some degree plus y to some degree plus or minus y to some degree, we can use y is equal to em of x. And what we're going to do is take the derivative of this multiple times and plug it into here. After we take all the derivatives, we get these values for our y's. So when we plug in our values into a, we get this emx in parentheses m squared plus 2m minus 3. We factor out the e to the x because all of our y's have an e to the x in front of them. So after we factor this, we can get m is equal to negative 3 comma 1. So that is our m values. So when we get our m values, we have to plug it into this. After we plug everything in, we get y is equal to c1 e negative 3 of x plus c2 e of x. And that is our general solution. It's general because we still have c's, constants, in our solution, so it is not particular. So for part B, after we get our y values, we can plug it in, and this is what it'll look like. After that, we can see that we only have one m, which means our y1 is equal to c1e negative 2x. Well, we need two m's, so from here, we need to use the reduction of order method. Using the reduction of order, this is the formula right here. After we plug everything in, we're going to get this. Our p-value is going to be whatever value is in front of y prime. If there's a value in front of the first y, we have to divide the entire equation by it, and that will be our p-value. Whatever this value is over whatever is in the front here. After we integrate the top part, we get this. We can bring the c1 down, so it'll be e to the negative 4x times c1. We can bring this c1 outside of the integral with this e negative 2x because it is a constant. After we bring out our c1, we're left with this. Our e to the negative 4x's cancel out, so we will just have a 1. And the integral of 1 is just x plus a constant, which is what we have right here. Splitting this into here, we get this part right here. We can see that this part is equivalent to this part, so our y2 is going to be this. From here, since these are equivalent, what we can do is just take this portion, what we have written here, and set it like this, and then just put a y in front of it. And that is our general equation. For part C, this is what our equation is going to look like after we plug in all of our y values. And there is no easy way to factor this part out. So what we're going to have to do is use the quadratic equation. So after we use the quadratic equation, we get this. And since we have a negative on the inside, we will have a I that we have to have out front. And then solving the square root, we're going to get I times 4. So we get that m is equal to 3 plus or minus to I. So since we have a complex solution because of this I, we need to use Euler's identity. Euler's identity, we need to use that identity, and that is this. For both of our m's, whatever value is not with the complex part is our alpha. Here we have our beta. And the same thing for this one, we have alpha and beta. So after we plug everything in, also this is supposed to be an alpha, not an x. I made a mistake and wrote x instead of alpha. But after we plug everything in, this is going to be our final answer. That is our general equation. So for D, we will plug in all of our y's, and this is what we get. So we need to factor this portion, and we get m minus 1 squared and m plus 1 is equal to 0. For this m plus 1 part, we can get this y1. For the m minus 1 part, we need 2 y's. However, we only get 1. So after we find the y for this, which is this, y2 equals c2 e to the x, we have to use reduction of order to get the second y value. So this is the reduction of order that we are going to be using to solve this. After we plug everything in, we're going to be left with this down here. This portion right here, we can move out here and we can solve it like this. We can say we have e to the x times e c1, and e to the c1 is just going to be c1. Since this is a constant, we can move it out in front of the integral. So that's going to place it right here with e to the x. And then now that we have that, we are no longer going to have this c1, so we just have e to the 2x over e to the 2x. We're going to take these out, and we're just going to be left with 1 dx. The integral of 1